Hello. My name is Kostas Galiotis, and I'm here to present the very last talk of the session. And this is on the Graphene Flagship, and in particular, graphene itself, and how graphene can revolutionize composites applications. Some of you may not be aware of what the graphene is. So graphene is a monoatomic material which has a very small thickness, just the size of an atom. And it has these amazing properties, very high mechanical properties, 1 terapascal, the highest stiffness, strength of around 100 GPa. It can also be stretched up to 20-25%. Very high electrical properties, better than copper, thermal properties, excellent properties. So it has it's like the holy grail of the material. And in terms of optical properties, it's almost transparent. It absorbs only 2.3% of light and has a very high electron mobility. Graphene and composites, really, you have to think all kinds of applications. If down on the left is application on structural materials because of the mechanical properties. But as you can go clockwise from the top, you have applications on energy, composites used in energy applications, composites used as electronic materials, thermal interface materials, quantum effects, nanoribbons. And if I skip the structure, we can go to sensors, gas barrier, and even in biotechnology. So there are a lot of applications, a raw material, which is graphene, into composites. Then composites is, which transporting graphene can be used in so many other applications. And in terms of patents, on the blue, it gives you the patent graph for graphene itself, and down below is the graphene composites, has now leveling off, but still we're talking about at the peak 2,000 patents a year, and this, of course, refers to graphene composites. Of course, just prior to the pandemic, the most important application areas were aerospace and defense, but also automotive is quite prominent there, wind turbines, etc., etc. Even in civil engineering, it goes into concrete. Today, we talk about graphene polymer composites in particular. Novel manufacturing processes have been developed. It's a lightweight structure, lightweight materials we're talking about. And multifunctionality is the key word for this material because it combines so many different properties. As I said, mechanical, electrical, thermal. Graphene Flagship is one of the largest network of funded research in Europe, 170 establishments, and had a duration of 10 years. It's coming to an end this year, and with a budget of 1 billion euro. A lot of things have been developed over the last 10 years. I will just show you some examples. Master batches. You can put graphene into master batches, and you can transport. Because it's a nanomaterial, you have to transport it in a very safe way. So master batches have been developed, particularly from a company like Avanzare or Bidimensional. The first one is Spanish, the second Italian. These companies have been actually started at the beginning of Flex, but now they are developing in a medium-sized SMEs. Microfluidization is another way of processing graphene in a safe manner. This is a slide from University of Cambridge. Filament 3D printing, you can actually add graphene into a polymer. This is what we're doing in Greece, University of Patras and Forth in Patras, where I come from. And you can make and you can build all kinds of heating sort of devices using the 3D printed fibers. Because of the graphene being there, that is bestowing thermal properties and heat to the material. So other innovative applications, which is I particularly have chosen this as a very important application, which is the fire retardancy. This is, again, the same company, Avanzare, that has done this work. You will see on the right, graphene added to a material, it actually lowers the intensity of fire, delays ignition, and helps to form a protective char. Is by far the best fire-resistant material to be used in polymers. Much better than any other and less toxic than any other additive that stops fire. And you can see an example there, which you try to burn a graphene composite knob handle. You will see you can never burn it. And on the right, you will see combo fiber material. This is the heat release rate prior to adding graphene, and then adding graphene. This is on G paper. G paper is a graphene paper that's produced by another company that's been developed, Nanessa, which is an Italian company that produces graphene paper that can go into, and you will see another application of graphene paper in a minute. So you will see by adding that paper, then the heat release rate goes right down. EMI shielding is another area. It's very thin, absorbs radiation. So if you divide the thickness, which is very important, and the size of the material, you will see on the right there that the effective EMI shielding is much better than any other competing structure, even Maxins or CNTs, etc. And this is work has been done from us, from our own university in collaboration with CNR in Italy. Very important application, which Airbus helicopters is leading within the flagship. We have projects within the project, in other words, is the heater mat. This is a composite structure that will be added and is added to other composite structures, and by just turning a switch, it heats up that material, that section, and you melt the ice on a helicopter blade or on airplane, etc., etc. This you will see, for instance, you will see the structure on the left and how it's heating up. Joule heating is very good. Graphene is very good at that because of the free electrons that it has in the structure. So you can heat up. The current is really is in square in Joule heating, so it is a very effective Joule heater. And this is what we're developing within. I'm sorry, I cannot say more than that on that, but it's a rotor blade demonstrator that can go on an aircraft. Other applications, humidity sensors. You can add graphene. Graphene is very sensitive to the presence of water, and you can 3D print a sensor which is very good, operates very high sensitivity and fast response. Pressure sensors. These are again composite structures which are in the form of tapes. You can go around your neck or your hand and monitor blood pressure and other things. It's very lightweight and very, very interesting. The first one, the humidity sensor, is used on the heater mat applications that goes on an aircraft. Other things which are commercial products, over the years, maybe you've seen it, the shoes insole that provides thermal dissipation is very good and very comfortable. The helmet, the Momo design, which is designed by IIT in Italy, improved impact. The bicycle tire of another Italian company, Vittoria, and this goes on the tire itself, replacing carbon black with graphene. It's another very important area which gives better wear than the carbon black. Another completely unrelated to this is using graphene as a coating. We have ourselves put it on artwork because it stops UV radiation, destroying the artwork. Because we're in Paris, artwork is important, and it does not allow humidity to go into the artwork. You can develop coatings like that, composite coatings, like on metals, on other materials, etc., because nothing permeates graphene, not even helium. So it stops water, other in fact, toxic substances, etc., etc. Finally, just some examples. This is the rear empennage of an Airbus structure with some the heater mats on the top, some stiffened leading edge. They can show you that graphene can go into larger structures, carbon fiber structures, and it gives, of course, adds mechanical strength and stiffness. And in a way reduces weight because you don't need to use so much resin, because graphene can do some of that work. And other applications is stiffened panel by the rudder of the aircraft and permeation barrier. That's very important also for automotive as well as the aerospace structures. That's just the last slide, which is, this is a 100% at least on the exterior carbon fiber car. This is the Dallara automotive car, which is on sale, but also Dallara is manufacturing structures for Formula One cars of other companies like Ferrari, for instance, Lamborghini, etc. So we add graphene into structural parts, which can be the underfloor of the car, on the panels, the exterior panels, and on the internal panels. That gives damping resistance, anti-rattling resistance, and of course fire resistance, which is very important for sports cars. So it doesn't set to fire straight away. So that's from me, and Francesco Gaza now from Fiat will present to you another application. Take a chair.
So thank you very much. As Kostas said before, inside the Graphene Flagship, which is a European project, we have projects inside the project. And now I am presenting to you one of the projects inside of the project, which is led by the industrial company, which is CRF. Just a small introduction about CRF. CRF stands for Centro Ricerche Fiat. So historically, we are the Fiat Research Center, but now we are almost integrated in the new Stellantis organization. In the product development phase, we are responsible for innovators as material, processes, and methodologies, all inside the company. By myself, I'm a materials engineer, so I'm responsible for new materials inside the company. And in fact, we represent Stellantis in the European national collaborative projects, joining pre-development, and we promote networking action. And that's why we are in the Graphene Flagship from day one, in order to be able to put the innovation of the Graphene Flagship inside our vehicles. You see in this slide, these are the motivations that lead the automotive industry to build up new material. This is very generic. I won't enter into detail. But you see these are the 6 megatrends for the e-mobility of the future. And in fact, all of that can be addressed by using the right innovative material. And that's why we are here. Just for a further example, this is a slide that compares the 1977 Alfa Romeo Giulietta with the same car, so Alfa Romeo Giulietta of 2010. For sure, they are two different cars, completely different cars, but they have the same name, they are in the same, more or less, range of dimension. And in fact, you see in the chart that the 1977 Giulietta was a lighter car than the 2010 Giulietta. But the weight that we added during the year makes the 2010 Giulietta a faster car, a car that has a better carbon footprint, a car that has less fuel consumption, and a car that is safer. But in fact, it is heavier. And you see the distribution of the weight. In fact, we worked a lot on the engine in order to make it less consumption in terms of carbon footprint and fuel consumption. And we increased the engine system weight by 20%. We also worked a lot on the body-in-white component, on the body-in-white material, in order to make everything safer. But instead, we had a weight increase by 30%. But nothing like that can be compared on the weight that we had to increase in our vehicles in order to address what we call electrical, electronic components, and comfort components for interiors. So for sure, during the years, the market has evolved. So you want a car that is very comfortable with a lot of electrical, electronic devices. But all of that led to a very high increase in the vehicle structure. And what it is increased in specific is what we call density of function. So you want new function every day for your customer, and each of these functions are busy inside of the vehicle. The vehicle has a straight volume, and we have to fix all of these things inside our vehicle. So we need to decrease the density of function. And in order to do that, the only way is to use multifunctional components. So we want to use, in this case, graphene, in order to have something that we call a multifunctional component, a multifunctional material that does multiple things, so we can decrease the density of function. And please take in mind that this example is only for cars that are from ICE, so internal combustion engine, and you have to take into account that we are moving to electronic and electrical vehicles, so weight is more and more important. So in fact, this is the project inside the project that we developed during the Graphene Flagship. It is called G+ board, and in fact, it uses graphene-related materials in order to have a dashboard which has two multifunctional components, one steering wheel which can be heated, and a dashboard drawer with sensoring inside. In the specific, we are using, in this case, graphene for the two applications in two different ways. For the glove box, for the dashboard drawer, we are using an engineered PP, which is filled with graphene inside. The graphene inside, if you put a small amount of graphene inside a thermoplastic material, you won't change their mechanical or thermal properties or electrical properties, because it is very difficult to disperse the graphene inside thermoplastic. But in fact, if you activate some of the part of the material with a laser track, like in the video that I'm showing, you can write directly on the plastic an electronical circuit. So in the tracks, the polymer becomes conductive, and you can build an electronic circuit directly on the plastic. No metal, anything else, completely recyclable. And in fact, you have a metal wearing replacement, so you have less weight on board, you have less fuel consumption, and you have easiness of recyclability because everything is plastic. Of course, the full control on the value chain is essential, and in the next video, I will show you which were the industrial steps that lead to our demonstrator that we have here at Jack presenting. You see there was a lot of industrial phase that was the identification of the material with the best performances, so you have to choose the right graphene for the right application. There was a manufacturing phase in which we mold hundreds of drawers in our plant with the doped material with graphene. And then with these drawers that are industrial part, we had to elaborate the way how to produce the electronical circuit, how to put it. You see here, there are different areas, a bigger area that works as a sensor, so as a button, and a small area that is useful to transmit the signal to the overall of the drawer. And then we tested this. We updated our manufacturing phase in order to have the best solution. And now we are preparing 15 final demo drawers with the best solution overall defined. And then we are moving to the old manufacturing phases that are performed typically on traditional materials. So we are foaming it in order to have an aesthetical surface. And this foaming is performed only on the aesthetical part. And in the meantime, you also have to think about the electronics. So the rear part of the drawer has an electronics that you need to fit inside it. So you see there is an electronical circuit inside the component that enables the switch on, switch off that says to the CPU open or close the drawer. And then there is the validation, the completion first of the manufacturing phase, so the assembly of the overall component, and the validation phase in which you validate the component from the comparing to the traditional one in order to be sure that the properties are exactly the same. You can see here a video of the first demonstrator. You see there are still some holes. This is not the final one. But in fact, you will see during the video that if you touch the drawer in the right area, the drawer opens. While if you touch it everywhere else, there is no signal transmission, so the plastic is completely isolating in the other areas. So you can have a selective opening only in the area that you want. For the steering wheel, the application is different. In this case, we are not using graphene for their electrical properties, but for their thermal properties. In this case, you are filling with a GRM doped layer, a leather skin, synthetic leather skin. So you are doping an additional layer on your commercial product. And in this case, if you heat it by Joule effect, as Costa said before, you will have a spread of the heat very fast and very homogeneous. So you have a surface which is very hot in less time than the other one. You have a reduced thermal load, and you have introduced an electrical properties inside of your component. So you have a multifunctional steering wheel. I can show you also in this case a video that represents all the manufacturing steps that we did in order to reach something that is very, very useful for the industry and something that is quite ready for the industrialization. You will see some subtitles. This is the one of the demonstrators that we have here at the fair. You see, this is the steering wheel that we have. In fact, we introduced graphene, as you will see in the video, inside a PU in the precursors. You mix it. The graphene is the black powder. You mix it. And then with the same manufacturing technology, which is made by synthetic leather, you have a roll, which is made of the classical layers and plus a layer of graphene inside. And this roll can be adapted to each steering wheel depending on the dimension and on the 3D, dimension of your steering wheel, can be wrapped exactly in the same way of a traditional steering wheel because it has the same flexibility. So it is metal-free, and as shown before, if you attach current to the electrodes, you have a spread of heat which is very uniform for all the samples. This is only a sample. And you also have this, which is a plus. So if you cut somewhere the leather, in that area you won't have any electrical conductivity or thermal conductivity, but in fact, overall, the system is still working. So you see here, there are some notches that are made purposely. And this is the comparison between the traditional one, in which you have wire copper. You see here, this is the traditional technology, so you have a lot of wire copper inside the skins. And this is the comparison of the two steering wheels. On the upper part, the traditional one, and on the lower part, the new graphene one. You see that at the traditional one, you are spreading the heat from the copper wires to the other part of the component, while on the new graphene steering wheel, you have a better distribution in less time and with higher performance in terms of energy absorption. So you have a heated steering wheel in less time and with less energy consumption. So, in conclusion, owing to its extraordinary properties, you see graphene has attracted different players in all our industries levels, at different levels, as Costa said before, aeronautics, we have automotive and all other different stuff. We have lightweight we can make lightweight components that are composite and that are also multifunctional, you see that we are now ready to have large quantities of graphene. We are talking about ton scale, so we are now in the industrial phase very well. And in fact, you see that there are very different kind. You can also have electronics, healthcare, and different kind of application. And specifically in the automotive, we tested, and we are very close to the industrialization of two different implementation of the graphene for having two different kind of multifunctional components. And you see, we are only using the thermal and electrical properties, but more is yet to come because you see, there are a lot of stuff that can be done. So thank you very much. And if you want to see these, some of these demonstrator and more, then we are at Hall 5 M75. So please visit us.
Since it's the last talk of the day, I think the organizers allows us to invite you to questions. If you have one or two questions, we'll be happy to answer them. I don't see any hands. So thanks very much for coming here. Thank you.
Thank you.